All right, so topic 5 today. Topic 5 is a short one, and it's kind of a little bit of a hodgepodge of things, but it's talking a little bit about laboratory methods around water quality and field sampling methods. And some of these lab methods we've actually talked about in the lab already. And so I've kind of put all these things sort of in one little mini lecture. And I don't know, maybe it should have been done at the beginning of the course, maybe not, it doesn't really matter. There are a few things though we're going to talk about today that are totally relevant to this week's lab on Thursday. One of the techniques in particular is very, very important. And so I think in some ways the timing is pretty good. We're going to be talking about spectrophotometry is kind of what we're going to talk about on Thursday's lab. And there's a whole bunch of field sampling manuals and things out there. And what I want to do is mostly just cover the basics. Every company and lab you're going to work for might have their own little protocols and systems around it, but there's a lot of things that are relatively basic and standard, and we'll get to those in a few minutes. So first thing I want to talk about a little bit is instrument calibration. So this is something we've done now. We've calibrated the pH meters and the conductivity meters. We've also used the dissolved oxygen meters. We did not calibrate those. The calibration for those is not done all the time because it's kind of expensive. But basically calibration, as we've gone through before, is really just comparing an instrument readings to a standard or several standards, and then adjusting the instrument so that it is reading other readings properly. So you can see in this example here, you can see the probe is put into the pH 7 solution. So what you do is you hit your calibration button or your standardized button, and you're telling the instrument, this is 7, read anything like this as a 7, and it gives it basically a baseline to do all its other readings around. Because really this probe is not reading pH. The probe is actually reading some sort of electrical voltage based around the ions and the chemistry in there. And so it needs to know exactly how to translate that reading to the appropriate pH. So calibration is pretty important. As you've seen in the lab, typically what it means is you're measuring some sort of standard, and hopefully the idea is to be relatively consistent. And you want to make sure that your instrument is reading things properly. How's calibration done? I think we've kind of talked about this already. And sometimes we calibrate because it's actually recommended by the manufacturer. And this is the kind of thing that, let me just take a look on the next page here, when you should calibrate. Kind of depends on the device. pH meters, they should be calibrated relatively frequently, basically every time you use them. Other meters, it might say annually, it might say monthly, kind of depends on what you need. The conductivity meters, for example, I don't think they need to be calibrated every day. I think it's recommended weekly or monthly or something like that. But it's good to know how to do them, and the solutions we have are relatively cheap, so it's good to know how to calibrate them. Sometimes the manufacturer is recommending more often, or sometimes there's a standard in the lab or for the procedure that says it must be calibrated this many times, and that type of information might actually be recorded. You can see down at the bottom, there's other reasons why you might calibrate. Sometimes as instruments get older, they get more finicky, so it's more important to calibrate them. And the hidden costs, right? If you want to make sure that your value is accurate, you want to be saving your employer time and money, right? If there's some question as to whether the instrument was calibrated, then that sometimes can become a really big deal. So there's some things to think about. Like I said, often there's a variety of reasons why you might calibrate that go down to either technical reasons around precision and accuracy, or sometimes other things, legal or manufacturer type of recommendations as well. Okay, so that's kind of all I wanted to say about calibration for now. What I want to do though is talk a little bit about UV visible spectroscopy. So this is a technique we're going to be using on Thursday. And so you can see it says there on the slide, it says, you know, what is it about molecules that allow us to see them? Okay, so that's just something to think about, right? What gives it color? And here's the answer, is that molecules can absorb, not all molecules, but many molecules can absorb light in the visible region of the spectrum. The visible region of the electromagnetic spectrum is what our eyes see. And so if things can absorb in that region, they're going to have color, and we're going to see them as colored. I see there's a typo that should say 250 to 800 nanometers. That's approximately the visible spectrum. Now, there is spectrum outside of that. Some molecules absorb in the UV range, some absorb in the infrared range, and sometimes that can affect their color as well. But generally, those are areas that our eyes can't see, although we can detect using instruments, of course. So this is the whole idea behind spectroscopy. I'll show you a video here in a minute, but let me kind of explain what is going on here. I guess what I meant to have is this animated a little bit, so you can just see part at a time. But here's the idea behind spectroscopy, right? Is you have a solution, and there's a molecule in there, and it has a color. And we can use an instrument to detect that color. And why is this useful? We'll talk about that in a minute. But this is showing the basic guts of a spectrophotometer, which is the instrument that does spectroscopy. So notice here you have a light source. Okay, so you have a light source right here. Okay, so that's usually a light bulb. It could be a laser or something like that in an expensive instrument. You have your sample. So notice your sample is in it's kind of a squarish shaped test tube called a cuvette. They're usually plastic and disposable. And then in between, you can see you have a system, and usually you're selecting a particular wavelength. So maybe 525 nanometers or something like that, right? And that's what's going on here in the middle. It's just selecting a wavelength. There's different ways to do it. You can see this is focusing the light into a prism. The prism separates it into a rainbow, and there's a little slit that's letting one wavelength of light go through. And then on the other end, there's a detector. Okay, and so the detector says how much light has gone through, and you can get a reading in the end. So I'll show you a quick little video here now. It's a 1-minute video that kind of talks about the guts of this, and then we'll talk about the applications of this. So here's the video. This one tends to be a little loud. I'm going to make sure that if it sounds loud, I'll try to reduce the volume a little bit. Just warning you, whoever recorded it, they made it loud.
Here's how a spectrophotometer works. A lamp provides the source of light. The beam of light strikes the diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector. Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample and converts this information into a digital display.
All right, so that's a quick little blurb about the guts of what's going on there. So basically you have this idea where you have light going through a sample, and you're measuring how much light is going through a sample. And so
here's how a
sorry, there we go. And so what you can read is something called absorbance. So absorbance is how much light the sample basically absorbs or takes in. And molecules that absorb light, like I said before, are colored molecules. So you might be familiar with chlorophyll. Okay, chlorophyll is found in plants, and of course it is a green molecule. There's actually 2 types of chlorophylls in plants, chlorophyll A and B. You can see there's the structures there. And so it turns out that they absorb light. You can see over here, right? So over here is the blue area of the spectrum. I should say blue, there we go. And they also absorb over here. And this is the red area of the spectrum. So what is left over? Green. So this is kind of how things are colored, right? Whatever light they don't absorb, is the light that is reflected or transmitted, and these things look green. So we can take advantage of this property, and there's literally hundreds of applications around spectroscopy, and it's really kind of mind-blowing how many ways people use spectroscopy. But what I want to do is talk about how we're going to use it in the lab, and probably the most common way that this type of spectroscopy is used. Here's another example. This is beta carotene. Beta carotene is an orangish reddish pigment that's found in all sorts of vegetables, such as carrots and tomatoes. And there's actually a few different carotenes. There's the structure there, and you can see it's absorbing mostly in this kind of blue ultraviolet range. Blue, we'll call it blue ultraviolet range. And what's left over is, of course, all the red and yellow and a little bit of green. And you get all sorts of different colors of orange and red and those kind of things in this. I know I have another example or two. Here's another example of a molecule. This one absorbs in the ultraviolet range of the spectrum only. So if you had a solution of this, it would not show any color. But the point I want to make is that this is detectable by the instrument. And you can see this instrument is reading basically an absorbance maximum of around, I don't know, 230 nanometers. There's some more compounds there. We have beta carotene again. We have beta cyanin. That's the purple color in beets. Ibuprofen. That's we call it Tylenol is the name brand, and copper sulfate as well. So you might notice that a lot of these compounds have what is called conjugated double bonds. So notice we have a double bond, single bond, double bond, single bond, double bond. That's what a conjugated double bond is. And so to throw a little chemistry at you, conjugated double bonds are loaded with pi electrons, and they have resonance. And when you have pi electrons with resonance, these are really good at absorbing light in the visible ultraviolet range. Copper sulfate does not have that. It absorbs for different chemical reasons, but it is a colored compound. So I just wanted to show you that one as an example. So notice this says applications, and it says here, this can be used to detect the quantity of analytes in solution. So this kind of makes sense. If you have a solution and let's say you have some, I don't know, purple Kool-Aid, right? And the purple color is very light, then you probably know there's not a lot of Kool-Aid powder in there. Whereas if you have a really dark color, you probably know that there's a lot more powder in there. It's the same thing with all of these compounds. If you have a high concentration, you have a darker color. If you have a low concentration, you have a lighter color. Now, our eyes aren't very good at quantitatively determining how much is in there. If I have some beet juice, I don't know how much pigment is in there. I have no idea. I just can say it's purple. But we can use our instrument to do this kind of thing. And the way that we do this is something that's called Beer's Law, or the Beer Lambert Law. Two different scientists, I think they actually worked independently. Most people call it the Beer's Law, but Beer Lambert Law is also acceptable. And what it is saying is that absorbance and concentration are directly related. So notice the other two parameters. E is a constant, which is going to be different for every compound and temperature. And L is the, we have those little cuvettes, right? Remember the cuvette, it kind of looks like, see if I can draw a square little test tube. There's my little square test tube. And it's basically the width of that test tube. And they're all standard 1 centimeter exactly, every single one that you buy from the manufacturers. So really what you're looking at is absorbance is directly proportional to concentration, and there's a constant involved. And that's all we need to know. And that's what the Beer Lambert Law is all about, and that's what we're going to take advantage of on Thursday's lab. So let me show you a little bit more about how this might work. So on Thursday's lab, we are going to be looking at iron in water samples. Now, iron, unless it's in like really high concentrations, you might not even know it's in there. So we want a nice sensitive technique to detect iron is what we want to do. And it turns out there is a colorized indicator. So indicators are not just pH things. There's indicators that will bind with calcium, as we saw in lab 1, and this is an indicator that binds with iron 2 specifically, orthophenanthroline, I guess. And notice it is a colorless compound. And you mix it with iron and you get this thing over here, this complex, and this complex is orange-red. And so now that we have, and it mixes in a certain ratio, and basically we can use this now to quantitate the iron if we have an instrument such as a spectrophotometer, okay? So let's take a look at how we might do this. Step 1 is what you do is, sometimes you might call this a calibration curve, right? So going back to calibration that we talked before, we need to know, in the case of a pH meter, the instrument needs to know what particular voltage corresponds to a particular, pH or something like that. And that's part of the calibration process. And whoever programs the software inside of the instrument has all that sorted out, okay? And you just need to hit that standardized button to say this is 7, and then there you go. A calibration curve is where you are doing this I guess manually. We're not looking at a voltage, but we're looking at color. And what we want to know is this exact relationship. We don't always know the constant. In fact, in many cases we don't. So this is the kind of thing that you have to do, almost every time you're doing this kind of experiment. So you can see a calibration curve or a standard curve. We'll call this standard curve is the usual name. Standard curve. It's basically where you take some known solutions. So you make up a dilution series of, in this case, different concentrations of iron. So this is going to be our first step, in fact, is we're going to get some volumetric flasks, and we're going to make some different concentrations of iron. And then you can take the absorbance readings and you can plot it. And it turns out that much of this relationship is linear. So this is what my standard curve might look like. So in this case here, it looks like I made a 1 part per million, a 2, a 3, a 4, a 5, a 6, and so on. I'm not going to have you make 10 solutions. That's a lot of pipetting, but that might be something you may do for a more important experiment someday. So this is kind of step 1. You need this curve. And so at this point, you have a direct relationship. So what you can do is you can figure out the equation of this line. So you may remember the equation of the line is y equals mx plus b. This here goes through 0. So it turns out that y equals mx. So m is the slope. And of course, y is absorbance. So absorbance equals the slope times the concentration. And that's it. So in this case here, it says here we have an unknown, for example. Let's say you take an environmental sample and it's from a groundwater well, and the absorbance is 0.25. And so you can type in, right? So the absorbance is 0.25. That means concentration. Concentration is absorbance divided by slope. Now, I haven't figured out the slope here on this one, but you can punch it in the equation. Or the other thing you can do is basically draw on the graph. So there's my 0.25 right here. I draw a line straight over to where it meets the trend line on the graph, and you can read it directly off the graph as well. The slope method is probably a little bit more accurate unless you have a really large graph and good grid lines or whatever, but both methods are basically how it's done. So it says here that this corresponds to concentration of 5 parts per million. And that's basically what we're doing for Thursday's lab. You're going to do make a standard curve. We're going to read some environmental samples, and you're going to make this nice graph and answer some questions around it. So it's a relatively straightforward kind of exercise, and it's a pretty common technique that's used in all sorts of chemistry labs for literally hundreds of different types of compounds out there. Okay, we're gonna move on from spectroscopy. Like I said, we're gonna see it in lab. That's on Thursday. And don't forget, we are in the chemistry lab this week. Okay, so make sure you come upstairs, bring your lab coat and your goggles. And this is the only other lab we have upstairs in the chemistry lab. So don't forget from chemistry. I'll try to remind you again on Wednesday, in Wednesday's lecture. So we did use something that is kind of similar to spectroscopy already in the lab. I think Christina and Kawit used this, colorimetry, and we used it to measure fluoride in water, I believe. This is kind of a really cheap form of spectroscopy, is colorimetry. It's really the same idea. You've got a light source, so here's my little light bulb. That's a light bulb. You've got a sample. In this case, it was in a vial, so there's my little sample vial right there. Okay, that's a terrible drawing of a vial. The light goes through. There's my light bulb, and then here's an eyeball. That's a detector, right? Don't know how to draw a detector. And in this case, it's not as sophisticated. There's not usually a prism to separate out the specific wavelengths and those kind of things. It's a much, much cheaper device. And a lot of these are field devices, and a lot of these are set to measure only one or two types of analytes. But it's the basic same idea. Light is going through, and it's trying to detect how much light is going through. And in the case of the fluoride, I don't really know what the compounds are added, but the solution looks pinkish in color, and the instrument is pre-calibrated to read fluoride only in this case of the instrument. Okay. So like I said, we're just kind of going to blast through this unit, and we'll probably in fact be done early today. The last part of this is I want to talk about field sampling. And this is something that in my life, actually, I don't have a lot of experience. I have a little bit of experience doing field sampling, but you know, my emphasis in my life has been more in the lab part of the analysis. But depending what kind of job you end up at, this may be a big part of what you end up doing. And I got to emphasize very strongly that it's important you know what your employer wants and how they want you to do it. What I'm presenting you here is kind of some of the standards of what most people are doing. Standards at a company may be much higher, and always check with the lab. So you can see the first thing it says, why do we sample water? Well, of course, it's probably pretty obvious. Sometimes we want to know if there's something bad in the water. But really, there's actually tons of reasons. A lot of water sampling is routine. Particularly water sampling is very common near facilities. They want to take a look at the water upstream and downstream, and they're going to measure it on a regular basis to make sure that nothing's getting in the river or whatnot. Sometimes we do it as part of an investigation. We think that there's been a contamination or something like that, and so that might be part of it. Of course, there's research and all sorts of other reasons. And another thing to think about is the goal of the sample. So when you sample water, you want something that is representative. And what does that mean? That means that you want something, if you're sampling the river, you want something that is representative of the whole river in that area. You don't want to be scooping up water, let's say, for example, a dog has just visited that nearby area and has urinated in the water, right? So you're not going to sample right where the dog just did his business, okay? Because then it's gonna have all sorts of contaminants in there, or anywhere where it's going to be too mucky or anything like that, unless that's representative of the river. So that's something to think about. And usually the idea is you're going to go deep enough away from shore and hopefully getting something that is, like I said, representative. And that's kind of an important part of sampling. So what kind of things are done, okay? One, and maybe the most important thing, is sometimes knowing exactly what is being tested for. And I'll explain why that is important in a few minutes. And understanding the procedures that your employer wants you to do. Two, making sure you have all the right equipment. Okay, so sampling containers. Sometimes sampling is done in glass containers. Sometimes it's done in plastic containers. Sometimes it doesn't matter which one it's done. And how much is required? Maybe a certain test only needs 50 milliliters. So they say, okay, I only need 100 milliliters. That's good. Other times they may want a full liter or more, right? Those kind of things are important. And any other equipment, right? Notice this basically says, talk to the laboratory, and the rest of the text says, before you go out. And most protocols are expecting you to store your samples on ice because that's keeping things fresh and refrigerated, and and then there's no worry about heat or anything like that ruining the samples. Again, it kind of depends on what you're testing for again. So here's kind of your standard container, okay? This one here, it looks like it's 500 mils, maybe that little bottle there. And like I said, it's kind of just a standard plastic container. By the way, I got some of this information from Maxim. They do a lot of water testing. And so a lot of these protocols are things that they've talked about that they want done with their water samples. So what can be measured in this? Most things, in fact, are measured from water in these standard plastic bottles. So you can see all of these things here, right? pH, conductivity, color, phosphates, sulfates, nitrates, nitrites, bromides, silica, acids, total and dissolved organic carbon, chlorine, total suspended solids, and so on. So this is for anything that's not fragile. Most of these things are not going to degrade or chemically react in the transit process and are actually good and stable for months or more, right? So not usually a big deal. Again, the volume sometimes is important depending on what the lab is looking at. You can see it's not requiring any preservatives. It's just saying less than 10 degrees. So typically it's assumed if you have something on ice, it's about 4 degrees Celsius, the sample anyway, not the ice itself. So that's your typical bottle. The other thing is, in a lot of cases, they're saying don't leave any air up there as well. Again, it depends on what you're testing for, and that's always a good question to ask the lab. There are special bottles for certain nutrients. So you can see this is a special bottle for certain parameters, such as ammonia or total phosphorus or chemical oxygen demand, and apparently has a little bit of sulfuric acid in there. And that's going to keep things from degrading as they're transported to the lab. So again, like I said, lots of special bottles for special measurements. Here's another one. This is for certain metals, and this has a bit of nitric acid. Looks like that should be an NO3 subscript, not superscript. The 3 should be at the bottom on the NO3 here. But a whole bunch of different types of metals. And again, I don't know the full chemistry behind this, but this is what Maxim is doing with some of their samples. There's a whole variety of them. Mercury is clear glass, so mercury probably reacts with the plastic for some reason. Volatiles and coliforms, and you can see that the coliforms contain sodium thiosulfate, which preserves the organisms so they don't die. And sometimes you have these amber glass, these brown glass bottles for certain organics that might get damaged by ultraviolet light. So naphthenic acids and certain pesticides and whatnot. Again, it really just depends on what's being measured. There's a whole variety of different containers out there. So a little bit more about preparation, kind of in terms of standard things. And again, this partly has a little bit to do with the company, right? Some companies may say you have to wear a hard hat and so on. Others may say hard hat is not necessary. Again, there's kind of things like that. But most companies nowadays are expecting people to have minimal of some sort of visible covering, such as coveralls or the orange vests and those kind of things. And often steel-toe boots are required and things like that. But usually gloves are kind of a good thing to have, just to make sure that you don't know how clean your hands are, particularly if you're out in the field. You're touching all sorts of things. You can see other information to get. Are permits required? Are you going into somebody else's property? All those kind of things. And one of the big part of this is having correct documentation, not just meaning permits, but that you have the documentation required for what you're doing on the field. Because often this is part of the field sampling process, is documenting what time, your GPS coordinates, and there's field measurements that are often taken as well, right? So one thing, one kind of protocol that I really would like you to know lots about is this protocol here called dirty hands, clean hands. Okay, so this is the kind of thing that you could get asked at a job interview. It's actually a pretty common job interview kind of question for the employer to ask people who are doing field sampling. They will say, do you know how to do dirty hands, clean hands? And a lot of people blank because they've never heard it before, but it's actually a pretty important kind of protocol. And I have a video I'll show you of some people doing it as well that actually explains it quite well. But the whole idea is you have two people taking the sample. So one person we call dirty hands, who's doing stuff that doesn't touch the sample, and the clean hands person, and that person is touching the sample. So what are they doing, right? So what is dirty hands doing? Everything that doesn't touch the sample, right? So they're writing things down, maybe operating pumps, maybe there's a shovel or a scoop or something like that that needs to be operated. They're touching the outer packaging or something like that, holding the cooler, you know, all those kind of things, right? The clean hands person, they are going to be the one directly handling the container. And often the container is put into a Ziploc bag to keep it fresh. And in many cases, Ziploc bags are getting double Ziplocked, right? So they would be touching the inner Ziploc bag and not the outer Ziploc bag. So they're the person doing the actual sampling. And they're trying to keep their hands clean from touching all that other stuff that could be contaminants. So what I'm going to do is, like I said, I have a really good video here shown by these women here, and it actually explains it very well. And they're going to, I can't remember, they're testing for mercury, I think, and it's on some ice anyway. So I'll play this for you, and they do a very good job of explaining the clean hands, dirty hands protocol. So I'll press play right now.
Hi, I'm Amanda.
And I'm Sarah.
Today we're going to show you about clean hands, dirty hands sampling for mercury.
Yay! Amanda, why do we do clean hands, dirty hands sampling?
Well, Sarah, when we're sampling for mercury and other trace contaminants, the biggest source of contamination is humans. And we want to make sure that we're not adding any contamination to our sample and we're getting an accurate measure of what's in the environment. Specifically for mercury, we're actually looking at the parts per trillion level, so we have to be very clean when sampling.
So remember, don't be afraid of your sample. Your sample's afraid of you.
That's right. All right, Sarah, shall we start?
All right, so I'm going to be taking on the role of dirty hands today.
Haha.
That means that my job is to physically reach into the cooler, put gloves on myself, gloves on Amanda, and then touch all of the different sampling bags.
Except, as clean hands, my job will be to touch the sample and the falcon tube, which is inside the bag, which you'll see in a second. Shall we begin, Sarah?
Yes, Amanda, let us.
All right.
Note that the gloves are all put in separate bags.
So Sarah's going to start and put gloves on herself. And because I'm clean, I cannot put gloves on myself because I will contaminate them.
Remember, Amanda only touches the sample bottles.
Nice glovemanship. It's kind of like being a surgeon.
It's true. Except it's colder here. Are you ready, Amanda?
I'm ready, Sarah. There's a lot of activity this morning here at Surf.
Now Amanda's already doing something she shouldn't be, and she's talking. When you're doing your sampling, make sure as dirty hands, your clean hands person is not talking. You can yell at them, you can point at them, just make sure they're not talking as much when the sampling's going on.
And why shouldn't I talk, Sarah?
You shouldn't talk because even breathing on the samples can introduce a source of contamination.
Especially if you're a smoker, which is super gross.
All right, now that we are fully gloved up, we are going to start taking our water samples. Again, my water samples are put into individual bags. As dirty hands, I can remember to touch the bags. And we are first going to start off with taking the samples. I have my triple six bottles here.
So again, I'm not doing anything because I'm clean.
And now, as dirty hands, it's my job to fiddle with the tubes.
But not touch them.
I push them up, don't actually touch them, and I pass them over to the mouth. Second sample.
So we repeat this process 3 times to collect all 3 samples.
As dirty hands, I want to make sure that I seal up the bags so that my samples don't pour and spill everywhere.
Now, Sarah, are we done?
Not yet, Amanda.
What's left to do?
Well, we haven't made sure that we're taking background levels of the outdoors. So that's what our field blanks are for. We want to make sure that there's no mercury coming out of the atmosphere that'll provide background levels for our samples.
We also want to check that what we're doing is clean and we're not contaminating the samples ourselves. So Sarah, what is a field blank?
Well, Amanda, we have 2 different types of field blanks. We first have a pour blank. So here I'm going to be passing you a tube that is empty and then another tube that is filled. Now what I want you to do is I want you to open up the cap on the tube that's filled with Milky water. Throw it into the cooler.
What's Milky water, Sarah?
The cleanest water you can ever have. It's cleaned at...
One might even say it's mercury-free.
Definitely mercury. All right, we did that too fast. But basically, you make sure you pour from one tube into the other one, and you make sure that while you're doing it, you're not talking.
So it's a test of how clean our clean hands, dirty hands sampling is.
The second blank is an open blank, and what we do is we open it and leave it open to the atmosphere for about 15 seconds. Now this is testing to make sure that nothing is coming out of the atmosphere that could be contaminating our samples.
And that we're also not contaminating our samples.
All right, close the bags again.
Little Rubbermaid box there with the 2 things on it.
There are mercury-free samples. Last but not least. Close all the bags, and you're done.
We're done. Yay! High five.
Okay, so hopefully you get the idea there. They're a little bit long-winded, but you can see how careful they are being, particularly something like mercury, which is in very tiny amounts. They want to prevent any contamination from anything, right? And that's the whole idea behind dirty hands, clean hands, which is sometimes a very essential sampling procedure when you're looking for very sensitive things. Not always required, but again, always check with your employer and or the lab. The lab is the one that will often tell you how they want things done. So here's some more sampling guidelines, right? Minimum, new gloves. Sometimes the water's filtered, pretty common kind of thing. So that should be for every sample, and handle in a way to prevent contamination. And that usually implies gloves and not breathing on it away from contamination sources and whatnot. Like I said, the other thing is something that is representative, right? So if you're measuring a potential pollution source, usually the standard is something upstream and something downstream to see if there's any difference, whether the pollution source is actually contributing to the water flow. Often the container is rinsed, not always the case. Some of those containers, as I mentioned, have they're pre-charged with a few milliliters of acid and things like that. So in that case, those containers are not often pre-rinsed, but normal plastic containers often are. So you would put the water in, rinse it, maybe, again, I don't know what that standard protocols are, but usually 3 or 4 times is pretty typical, and then fill it up. So in most cases, most tests, no headspace, meaning no water in there, or sorry, no air in the top of the container. The reason for this is that air has oxygen, and oxygen in some cases can oxidize certain compounds. So we're trying to minimize the amount of oxygen, just in case it does interfere with the samples. There are, again, exceptions, is that usually samples are thrown directly on ice. And as it's happening, paperwork is done at the same time, including something called chain of custody. I'm going to talk about chain of custody in a minute, which is important for legal samples. So I'll get there in a minute. Typically, certain tests are done on site. So the typical things that, in fact, we've done a bunch of these ones here already: dissolved oxygen, pH, temperature, conductivity. It's very typical to do those on site with field meters. And I think some of those things do change with temperatures and whatnot. And it's something that can be compared with in the lab. And they're very easy field tests with all the meters and whatnot nowadays. Generally, field notes as well are taken. So the time of observation, the GPS, those kind of things. And as I mentioned, chain of custody is something that I want to talk about in a minute. So let's just talk about that chain of custody in terms of what that means. Okay, so most samples is going to have some sort of paperwork involved, right? So you're going to have a container, it's going to be labeled, and there will be some paperwork that corresponds to the number on the bottle with where and when and what was sampled, those kind of things. And whatnot. And like I said, don't forget to consult with the lab what exactly they want. You don't want to have to find out that you were supposed to have done a pH measurement in the field and you didn't do that, right? Don't want that to happen. But some samples are what we call legal samples, okay? And so a legal sample basically means something that, that may have legal repercussions. So for example, a lot of the oil sands companies, they have to sample water. They have to do it legally, meaning that the records are part of documents that are going to be reviewed by government officials, and they want to make sure that everything was done properly to the book. And so there's some extra precautions around legal samples. Sometimes legal samples are part of investigations and things like that. And so it's important that those are done properly. Some companies do legal samples for all their samples. Again, it kind of depends on what's going on. But for legal samples, we must be able to prove in a court of law a chain of custody of that sample. And so let's get into what that looks like. So chain of custody is basically documentation that is tracking the sample right from the moment it was sampled all the way until it makes it to the laboratory. Making sure that it didn't get lost, wasn't left in the, in the, let's say, the back of a truck, and several people use that truck and whatnot. It's basically to say that we have kept track of this sample. No one has touched it or messed with it between when we took it and when we got it to the lab. And that's basically all it is. And so usually there's paperwork involving this. You can see there's some paperwork there. You can see every time the sample is transferred to a new individual. So sometimes the technician may be somebody taking the sample in the field, and they hand it off to another technician who's driving back to the lab. And this is where the paperwork has to say, okay, it was handed off from person A to person B, and so on. And then when the lab receives it, they sign off and say they've received it. And in many cases, the lab will actually put it in a locked fridge or freezer as well to make sure, like I said, to minimize that contamination. Or sometimes the lab itself is considered to be a secure zone or what. And so this is basically what a chain of custody is all about. It's really important because if chain of custody cannot be shown, then sometimes that sample is inadmissible. There's a famous case here of a baseball player, and he was investigated around a drug charge, and he tested positive. So yes, he took the drugs, but they could not prove the chain of custody all along the way. And so, and simply it was because there was the sampler didn't make it to the FedEx office in time, and he stored it in his basement and didn't document all this. And so there was no evidence of sampling and all that, but the judge overturned the results and said he's not. So you can see how significant this can be. You can imagine with any multi-million-dollar investigation and whatnot, how tight this kind of thing has to be. Notice it's talking about samples being sealed and whatnot. I'll show you how that might work. There are ways to do this. I thought I had some pictures. There we go. Here's some examples of coolers that are sealed with these custody seals. These are special types of stickers that you can't just take them off without ripping them. And then of course, I think usually in many cases, people will put their signature across that sticker to show who had done it and whatnot. And this is pretty typical. And there would also be seals on the Ziploc bags and also seals on the containers. So that would be a triply sealed sample, cooler bag and sample bottle kind of thing. what was this all about? You know, I guess we talked about this already. Usually there's ice, sometimes there's bubble wrap to protect glass containers and so on. And that's kind of how the sampling is done. Okay, I think that's actually it for this topic. Looks like we're at the end there. So like I said, relatively short topic, kind of a hodgepodge of a bunch of things in there around the lab, calibrations, and standard curves for spectroscopy, and a little bit about field sampling. So I guess that's it for today. I will see everybody on Wednesday. Thanks for coming out.